linear convergence, right? So we say that xk converges to x star linearly. This means that xk, let me put it this way. So this is xk. Oh, see, I'm trying to be consistent with the notation you have seen so far. So let me try this again. See, Ryan likes to put the iterates in the index in the top, right, for the iterates. So let me put xk converges to x star linearly. This means that if we look at the norm of x, say k plus 1 minus the norm of x star, this is less than or equal to some constant times the norm of xk minus x star, okay, for some c between 0 and 1. So that's linear convergence, right? That's linear convergence. All right. So superlinear convergence is much faster than this, right? So something is superlinearly convergent means that we do this not just for a constant, but the constant goes to 0 as well. The ratio of the difference between the current iterate and the solution and the next iterate, the next iterate and the solution to the current iterate, that goes to 0. So that's a lot faster rate of convergence than linear. It's called superlinear, okay? So that follows, again, from the fact that that is an inherent property of Newton's method. But it turns out that if we make a little extra assumption about the Jacobian, if the Jacobian is not just non-singular at the root, but if the Jacobian is Lipschitz, if it is Lipschitz around the root, if it is Lipschitz on a neighborhood of the root, then we actually get something that is a lot stronger than even superlinear convergence. We get quadratic convergence. So do you remember the example just a couple of slides ago of finding the square root of 2? How at each iteration we double the number of digits of accuracy? Well, that's quadratic convergence. Quadratic convergence basically means that the accuracy of our current solution doubles at each iteration, roughly. Okay? So that is a remarkable property of Newton's method. And of course, if you apply Newton's method to minimization, the same thing holds. It's just if instead of big F, you have the gradient of F. Okay? So this is, again, in sharp contrast to gradient descent that, under certain circumstances has only linear convergence. Okay, so quadratic convergence. So again, let me recap. Affine invariance, key property of Newton's method. So local convergence, superlinear and with a little bit more quadratic. That's the second key property of Newton's method. Okay? So I trust that it's only 25 minutes into the class, so I'm hoping that I haven't lost anyone yet. So see, if you get lost later, you got to see the main part. This is the main two attractive features of Newton's method. Let me pause here for a second in case there is a question or anything. It's the first time that I'm getting to know you, so any comments or questions? I'm assuming that if I don't hear anything, it means, well, we're cool with this. Speed up and tell us more. Yes?
So we never assumed any kind of convexity.
Oh, so here, that's a good point. Here, that's a very good point because, yes, for this local convergence statement, we actually don't even assume that we are dealing with a minimization problem. This is just for root finding. So that's right. We don't assume convexity. We just assume that there is a root. We start close enough to that root, and the Jacobian is non-singular at the root. That is an important detail, that the Jacobian being non-singular at the root. Yeah. Anything else? Yes?
So for the affine invariance, if I take one problem and then just scale it and the same problem and run both of them in Newton's method, the error rates for the two, the rate would be the same, but the value of the error would be different.
Oh, the value of the error will just, transform the same way. Yeah, so if you, yeah. So let's say if I were to multiply everything by 10 to the 8, then the error will be multiplied by 10 to the 8. But the rate at which the error goes to 0 will be exactly the same. Okay? Yeah. All right. Now, let me mention something. So there is this key, say, this is a qualified statement. This is local convergence. Okay, so this makes Newton's method look tremendously more powerful than gradient descent, and to a good extent that is the case. However, this is only a local convergence result, meaning that it only holds locally. It holds if we are sufficiently close to the solution, to the root, or if it is for minimization, to the minimizer. Okay. Now, I imagine you probably have seen this, but let me just state it for good measure. So Newton's method may not converge. Newton's method does not have, at least the pure Newton's method that we are talking about so far, does not have global convergence. So Newton's method could fail. Newton's method may not converge. And I'll show this via a converge. I'll show this via a simple picture, right? So suppose that my function, suppose that I use Newton's method for, this is for root finding, right? And my function looks something like this. For instance, think about the cube root of x. So suppose that my function is like this. Right? So if I were to start somewhere, let's say here, right? I should have drawn this picture before. I'm sorry, I didn't. That's kind of the picture that you're always supposed to draw when you talk about Newton's method. So remember what Newton's method does is look at the linear approximation of f and solve that, right? So if I'm here, if I'm somewhere around here, and the slope is sufficiently flat, then I'll go here, right? And then if I go here, the slope is sufficiently flat, I go farther. So this would be, suppose that this is x0. This would be my x1. This would be x2. Then here, I'll go along the linear approximation. This would be x3, and so on. So you can see that if you have that kind of shape, okay, if the function that you're trying to find a root of has that kind of shape, then as you apply Newton's method, it actually may diverge. Okay, so that is a limitation of Newton's method. We will see in a moment what to do about that limitation. Actually, I can ask you, what do you think we would do about that limitation of Newton's method? This is in some way, a problem of, say, using the pure Newton's method. Does anyone have an idea what we could do about that? Yes?
We could try a bunch of different start locations, maybe randomly.
Well, that's one possibility, to try something, to try different start locations. But is there maybe another hack that we can do to the method itself to avoid getting sent, off track? Step sizes, exactly. So we'll talk about that a little bit later. All right. So before we talk about that, however, I want to mention something that is kind of a neat measure of the progress of Newton's method. So this is called the Newton decrement. And I find this to be really cool. It's kind of related to the very first thing that I told you today earlier, this kind of quadratic functions. So the Newton's decrement is this quadratic term on the gradient. So we take gradient, Hessian inverse gradient to the power of 1/2. So that, we define that to be the Newton decrement. This quantity is going to pop up again, I think next time, and maybe, next week. So how does that relate to Newton's method? So if you think about remember, Newton's method can be seen as minimizing this, for minimization, right? We are going to talk about Newton's method for minimization. It can be seen as minimizing this quadratic approximation of f. So if you look at the difference between f of x and the minimum of this quadratic approximation, it turns out that when you plug in the minimizer here, which is exactly the Newton step, and then simplify things, at the end, the difference between f of x and the minimum value of this quadratic approximation turns out to be 1/2 the Newton decrement square. So, so that quantity, lambda x squared divided by 2, is an approximation to the duality gap or the suboptimality gap between f of x and the minimum of f. Okay? It's not exactly equal to this. It would be equal if the quadratic approximation were the same. It's just an approximation to the extent that the quadratic approximation approximates the function. Okay, so that's the Newton decrement. The Newton decrement also, so we define it in this way, right? Gradient, Hessian, inverse gradient. You can also, if you squeeze in the middle here, Hessian times inverse, you can also think about the Newton decrement as the Newton step times Hessian times Newton step. Okay? So observe, again, this is kind of really neat. The Newton decrement sort of relates nicely to these two expressions here if Q is the Hessian. On the one hand, you can see it as an expression like this where with the Hessian and with the gradients here, or you can also see it like this. Sorry, the other way around. You can see it like this where y is the gradient and q is the Hessian, or you could see it like this where x is the Newton step and q is the Hessian. Okay? So that's another interpretation of the Newton decrement. So it's the length of the Newton step, but if we are measuring it in that product, in that inner norm, in that norm defined by the Hessian of f. Okay. Now I'm not going to work out the details here, but it would be a nice exercise if we look at the Newton decrement for after we make an exchange of after we scale, then the same thing happens, namely that the Newton decrement for g at y exactly matches the Newton decrement for f at x, provided that x is equal to a of y. Okay, so we have that kind of also affine invariance in terms of the Newton decrement. All right. So let me talk about backtracking, and this has to do with this potential, say, flaw of Newton's method. Okay? The fact that Newton's method may not converge if we are not careful where we start from. So what we are going to discuss is how so Newton's method, as I have described it so far, is called pure Newton's method. So the step size is 1. So I guess back here, this, if I were to say qualify this maybe a little bit more, this is pure Newton's method. Okay, so the step size is 1. So because we may have this business of we may have to worry about global convergence. So if we were to implement Newton's method, it would actually make more sense to use some kind of line search. So this is sometimes called the damped Newton's method. We take a step along Newton's method. And something that is neat about Newton's method is that we always have an initial, candidate for what step length to use. That is, start with 1 and monitor the decrease in f. Right? If f does not decrease enough, then we take a less aggressive step. So what this means is we are going to take 2 constants, alpha and beta. So this is similar to the kind of line search that you saw earlier for gradient descent. The point of this type of condition is to ensure that the actual decrease in the function is at least a fraction of the decrease predicted by the gradient. Predicted by, by the gradient in that direction. So we would take, again, as an initial value, t equal to 1. And as long as this holds, then it means that the step that we are taking is too long. F is not decreasing. F is actually potentially increasing, or is not decreasing sufficiently, so then we take a smaller step. Now, this is guaranteed to eventually converge, eventually terminate, because the gradient with v, where v is the Newton step, the product of this gradient with v is precisely what I mentioned earlier as the Newton decrement squared. So the product is always negative, and therefore, for t sufficiently small, the reverse inequality has to hold for t sufficiently small. So that's backtracking. And here is an example of backtracking. In the homework, in the next homework, you're going to actually see the details of this. You will implement Newton's method, and then you will see before your eyes how this actually works. So it turns out that if you do Newton's method with backtracking for a logistic regression problem, it has this kind of behavior. If you were to compare it, say, in terms of iteration count with gradient descent, you see this different behavior here. Okay, so gradient descent exhibits something that is like linear convergence. Newton's method, even with backtracking, right, it exhibits something that is a lot faster. It's a much faster regime of convergence. So the next statement that I want to describe is a formal statement of the convergence of Newton's method with backtracking. Okay? And the statement is going to be in the same spirit as the convergence, the local convergence statement that we saw before, but it's going to include more bells and whistles, because now the method, the algorithm that we're looking at, is including backtracking. So it includes a few more moving pieces. So I understand that the usual protocol is to take a short break, maybe around this time. This seems to be a good place in our discussion today for that. So why don't we take, is it 5 minutes usually? Okay, let's try 5. Okay. Let's try 5. Let's try 5, okay? So let's try 5, and then we reconvene right here. Okay, so I think that's 5 minutes. All right, so here, this is just an example. And again, as I said, you're going to do an exercise in the next homework where you essentially play with this example and see how Newton's method actually performs. Okay, so let me recall for a moment. Let me go back here for a moment. Here, so this is the local convergence that we can. This is a very general statement that we have for Newton's method, even for root finding. So certainly, it also applies to minimization. And here, there are a couple of things that are a little bit maybe not fully satisfactory about this statement, and is that this is an existential result. Right? This is the kind of stuff that mathematicians like there exists some delta such that that works. But computer scientists typically don't care for that, right? Like, well, so what? That exists, but how do I know if I'm there? How? What does that mean in terms of an algorithm if I were to implement it? When do I know that happens? So that's a bit dissatisfying. And here, again, we need to ensure that this is Lipschitz, and then we get the quadratic convergence eventually. Okay. But the statements as written there, like the quadratic convergence, is not explicit about what k is. So the statement that I'm going to describe next tries to be more explicit about delta and k, essentially, or quantities that are like delta and k. So I'm going to describe the next statement. This is going to be for minimization, right? So we are going to do backtracking. This kind of backtracking, in principle, the backtracking makes sense if we are minimizing. It's a little more, it would be a little more difficult to make sense of backtracking if we are if we're doing root finding. But for minimization, the backtracking is based on this condition. And here is the statement. So let me spend a few minutes going over this statement. So the technical conditions that we are assuming are, so of course, for Newton's method to make sense, f has to be twice differentiable because we are looking at the Hessian. Okay? So this is, again, for minimization. So we're looking at the Hessian. And then we are going to assume a certain good behavior of the function. So we assume that the gradient is Lipschitz. Okay? The gradient is Lipschitz, which is somewhat similar to the statements, the technical conditions that you need for convergence of, say, gradient descent. We also assume that f is strongly convex. Okay? And this is not, granted a strong assumption. We assume that f is strongly convex, let's say, with parameter m. And then we assume that the Hessian also is Lipschitz. So if you think about the previous statement of quadratic convergence for Newton's method for root finding, the statement was assuming that the Jacobian was Lipschitz. So the Jacobian corresponds to the Hessian if we are doing so here the Hessian is assumed to be Lipschitz. So if we do backtracking just the way that we described before, okay, so there are certain constants alpha and beta. Alpha is so that we do backtracking as long as this condition holds, as long as we don't have sufficient decrease. And beta is how much we shrink our step each time that we backtrack. So if we do backtracking, right, if we do backtracking, then this is what happens to the convergence of the objective value. So this convergence is a little bit weaker in the sense that I'm bounding not the difference between the iterate xk and the solution, but only the function value f at xk and the optimal value. So for a while, before a certain threshold, the line search just guarantees that I make some kind of a slow progress. The progress is proportional to k. But once I cross a threshold, then I enjoy a quadratic convergence. So essentially, this statement here is a quadratic convergence statement. If you think about 2 to the k, ignore this for a moment and just think about 1/2 2 to the k. What that means is that, again, the difference between f of xk and f star, that difference, the number of digits of accuracy of that difference doubles every time, because this is 2 to the k. It's not just like 1/2 to the k. That would be linear. This is 1/2 to the 2 to the k. Okay? So this is the regime when we get quadratic convergence. This is the regime when we get quadratic convergence. So think about this threshold k0 as kind of what in the previous theorem was delta. K0 means after k0 iterations, now I'm close enough that the method is going to zoom to the optimal solution. Okay? So what is k0 and so this turns out to depend on a number of different, to depend on the constants, those constants L, M, and small m and big M. And also it depends on the parameters that I use for my backtracking, alpha and beta, in a more involved way. So here, the decrease here is something that depends on those parameters, right? And then the threshold here, the threshold is the number of steps until we get to this condition, until the gradient is sufficiently small, less than eta. where eta is that quantity. Once we cross that threshold, then we enjoy quadratic convergence. So there are essentially two phases here. The damped phase is when the gradient is still, say, bigger than eta, where eta is that thing that I described earlier. And when that happens, then the decrease from each iterate to the next is only bounded by gamma. And then once we get that the gradient is sufficiently small, that means that we are close enough to the minimum. Once we get there, then we enjoy basically quadratic convergence. So we have the gradient, the norm of the gradient, that size of the norm squares at each, after each iterate. Okay? Now, there is one more thing that I guess is not stated here explicitly, but if you were to, again, unravel this and see what happens to the algorithm, another thing that happens here once we cross this threshold is that the backtracking would not need to take steps less than 1. So eventually, when we are close enough to the solution, Newton's method becomes, even with backtracking, it becomes a pure Newton's method, and we get the quadratic convergence. Okay? So that is, again, a much more involved statement of convergence. So there are a few things about this that are a little more elaborate, and a little bit, say, maybe puzzling. So if you think about, if we think about, let me write down again the. So if you see the statement here, right? So yes, so to get say within an epsilon, if we want f of xk minus f star to be less than epsilon, and you play with these bounds, it follows that we need that many, at most that many iterations. So if we didn't have to worry about the damped phase, if we directly had the quadratic convergence, we would only have the second term, log of essentially something like 1 over epsilon. So the log of 1 over epsilon is the quadratic convergence. The initial part, f of x0 minus f star over gamma, that is the part that is due to the damped phase when the algorithm makes slow progress. So the second term there is what we call the quadratic convergence. If you think about, say, gradient descent, in gradient descent, under certain assumptions, you had linear convergence. So linear convergence means that to get within epsilon, you need log of 1 over epsilon. Quadratic convergence means to get within epsilon, you need only log of 1 over epsilon. Okay? And again, the quadratic convergence here, as in the statement that I mentioned earlier, is only local, meaning that a fast speed of convergence only holds when you have crossed a threshold. Okay? So something that is a little dissatisfying about the statement, right? The statement here is that the statement, so this theorem, depends on all those parameters, L, M, and yeah, all those things, in a not exactly simple way, even though the algorithm does not make use explicitly about L, small m, and big M. And again, let me point out to something that you have seen before. If you think about the, say, convergence of the gradient descent, in principle, the Lipschitz constant can be used in gradient descent, or in principle, the statement of convergence of gradient descent depends on the Lipschitz constant, but the step length also depends on the Lipschitz constant. Here, the algorithm does not depend on those constants, and yet the statement of convergence does. So that's a little dissatisfying. So there is a much more, how should I put it, sophisticated type of analysis of Newton's method. So let me for the next couple of slides, I want to mention something that I want to share a personal anecdote. This is actually what got me absolutely captivated into optimization back in the day, many years ago when I was in grad school. At that time, this was in the 90s, interior point methods were all the rage. So interior point methods is what everyone was talking about back then. At that time, if anyone dared talk about first-order methods, everyone would laugh at them. You know, first-order methods were thought of as algorithms that were forever forgotten. You know, interior point methods was the thing to do. Like, you know, interior point first-order methods were what maybe amateurish people did. Interior point methods, Newton-like methods, that was what serious people did. And part of the reason that that was in such vogue back in the 90s was because of this absolutely beautiful development that in some way is the backbone of interior point methods and is self-concordance. So self-concordance is a certain technical condition that was conceived, was discovered out of necessity to formalize the quadratic convergence of Newton's method in a way that is not as cumbersome as this. This is somewhat cumbersome. This kind of statement is a little bit cumbersome. So self-concordance was again, a certain technical condition that people realized that if functions satisfy this kind of condition, then that would make the analysis of the convergence of Newton's method be much more elegant, much more natural, and much stronger. So what is self-concordance? It's easier. I like very much the way that Boyd and Vandenberg define this. So if we have a convex function that is defined on an open segment of R, okay, so it could be a semi-infinite segment, for example, from 0 to infinity, or an open interval. Self-concordance is that condition, okay? It's that condition, that the absolute value of the third derivative is less than or equal to twice the second derivative raised to the power of 3/2, okay? So that's the definition of a self-concordant function, again, on a segment, an open segment of R. Now, if we have a function that is defined on an open domain of Rn, then we say that it's self-concordant if the restriction to any line in the domain is self-concordant, okay? So maybe I should write that down so that it makes sense. I didn't really write what that means, so I just wrote it in words. So what this means, that second part, what that means is that if we have f defined from D to R, okay, and D is a subset of Rn, open, this is important, open and convex, okay? So then we say that f is self-concordant if the following function, if for all, let's say for all x in D, okay, for all x in D and D in Rn, the following function, the function t, goes to f of x plus td, okay? So this is a one-dimensional, the restriction of f to one line, right? So this is like we have the domain D, we have x, and we have a line. And we are just looking at f restricted to that line. If that thing is self-concordant. Okay, where, again, for one-dimensional, self-concordant means this inequality here. Okay? So let me give some examples of self-concordant functions. So the simplest one, I mean, it's even simpler than the one that is there. So this is an example of self-concordant function. This is maybe the canonical example of self-concordant function is f of t equal to minus log of t. Okay? So clearly, this is f from R plus to R. So f of t minus log of t. You can quickly check. If you look at the first derivative is 1 over t, right? The second derivative, I guess it's negative 1 over t. Maybe I should do that real quick here. The first derivative is negative 1 over t, right? The second derivative is 1 over t squared. And the third derivative is, I guess, minus 2 over t cubed, right? You can see that indeed here, f in absolute value, right, is 2 over t cubed, which is exactly equal to 2 times f t to the 3 halves, okay? So that is the canonical example of a self-concordant function. That is the canonical example. But then there are a couple more that are really play a central role in 0-point methods. So these guys we are going to see again. You've seen some of this before, right? You've seen this guy before, I think. Not if you have, or shake your head if you haven't. You have, right? So this is called the logarithmic self-concordant function. So this one is defined in Rn plus. And this guy is, remember this Sn is the space of symmetric n by n matrices. And Sn plus plus is symmetric positive definite n by n matrices. This function, and there's a typo in my slide here, I apologize, this should be big X, okay? This should be big X. F of big X minus log of determinant of X. This is also self-concordant. This is kind of a cool exercise to prove. The first one is relatively easy to prove. The second one requires a little bit of matrix algebra, how should I say, matrix algebra gymnastics to prove, right, that the second one is self-concordant. I mean, it's not tremendously difficult, but it does require a little bit of work. So what's the deal with self-concordant functions? Well, one more thing about self-concordant functions. If you take a composition of a self-concordant function with an affine transformation, that is self-concordant. So for example, if we have, another example. If we take, say, A, right? Suppose that A is A1 transpose up to AM transpose, right? And B is B1, BM. Then this function, let me call it f of x. F of x would be minus the sum from, say, j equal 1 to m of the log of AI transpose x minus b, aj, bj. This is self-concordant. Because this function is essentially this kind of composition. Is that type of composition with this a and this b, okay? And g, where g would be the logarithmic barrier function. So what's so special about self-concordant functions? So these two guys who are essentially absolute giants of optimization, right? They are like legendary, almost mythical figures in optimization, Nesterov and Nemirovsky. They were the ones who conceived of this idea of self-concordance. And again, self-concordance was conceived precisely to make Newton's method, right? You would imagine this is really a remarkable fact, right? Newton's method is an algorithm that is hundreds of years old, and yet, as recently as only a few decades ago, someone manages to make a breakthrough about Newton's method, right? And a pretty important one. It turns out that this requires a little bit of more careful machinery and stuff, but basically, the statement is that you get that kind of similar quadratic convergence, but in a way that is only dependent, that the only constant that comes up here in the statement only depends on how we do the backtracking. Okay. So this is a much stronger type of convergence analysis of Newton's method. Something else that I'll mention probably next time or in one of the future lectures is that that one I want to do in some detail is that I can give conditions, much more explicit conditions for verifiable conditions for when we are close enough so that quadratic convergence will kick in. Okay, so self-concordant is a very special property that allows me to formalize the good properties of Newton's method in a much more explicit fashion and with much stronger results. And again, for now, this is going to come up again, but for now, think about self-concordant as that technical condition. The two canonical examples are these. And the key fact about self-concordance is that it makes Newton's method work well. Yes?
Does the proof require F to be self-concordant?
Oh, of course. Yes, sorry. Yeah, I should have stated that there. Yes. So this is for self-concordant function. So I guess an assumption here is, we are assuming F is self-concordant, right? And we are applying Newton's method to minimization of F. Okay. And of course, we are assuming that the minimization problem is bounded so that it makes sense. So think about it as, for example, if F is a function like this, where this guy here, this set, so this function here would be defined, this function would be defined in the set X such that AX is bigger than B, right? Is defined from there to R. So if this set is, for example, the interior of a polytope, then the minimization of F would be a certain point that is kind of the most interior point in that polytope. And this is the statement of how Newton's method will behave for that minimization. Okay. All right. So let me mention a few. I have already alluded to some of this, but let me be more explicit about some kind of parallel between Newton's method and first-order methods. So Newton's method, often Newton and Newton-like methods are often referred to as second-order methods. Second order because they use Hessian information. So the comparison between second-order and first-order methods. So in terms of, say, memory, right? Newton's method, in principle, if we didn't take it into account, if we didn't take advantage of sparsity, in principle, it requires that we look at the Hessian, right? So that's an n by n matrix, that is n squared. Whereas first-order methods, we only look at the gradient, which is n, right? So there is that trade-off. Newton's method requires n square memory, or order of n square memory, as opposed to first-order methods that require only order n memory. Okay, so the memory requirements are quadratic on the dimension of the problem. And then in terms of computation, if you think about what Newton's method needs to do at each step, right? So Newton's method, what does it need to do? It needs to do this, right? Hessian inverse gradient. I always like to make this joke in my PhD courses or my graduate level courses. How do you compute this Hessian inverse vector? This is how you do not compute it, right? You do not compute the inverse and multiply by a vector, right? That is considered a numerical sin. You never do that, right? Or you rarely do that. As a rule, when you need to compute this, what does this mean? Solve a system of equations, right? Solve the system of equations Hessian times some, delta time equal this guy, right? So this means that in terms of computation, each Newton step requires that you solve a system of equations with the Hessian as in the matrix. So again, if we didn't take advantage of the structure of the problem, in principle, that is an n-cube flops operation. Okay? If we were to, say, look at that as a dense n by n linear system. Okay? By contrast, if you think about gradient descent, gradient descent, we do not need to solve any system of equations. We just have to compute the gradient and maybe do some kind of adding of n-dimensional vectors. So in gradient descent is, again, linear. So in terms of both memory and computation, Newton's method is, has a steep cost relative to gradient descent. Okay? Now, the backtracking is not additional, essentially no overhead, because the backtracking is just an evaluation of, it's a simple linear type of computation. So that's really not significant. Now, conditioning basically has to do with the affine scaling. So if you have a problem that has, say, if you have a function that has, so suppose that we have that the level curves of f, suppose that they looked like this. Okay? If they look something that is kind of like ellipsoids, that is great news for Newton's method. Essentially, that, if we then were to stretch things, remember Newton's method is indifferent to stretching. This would be not that much different than, so this would be about the same as if we had them, if the level curves were like this. Now, if you are doing, so this would be the same for Newton's method. Now, if we are doing gradient descent for a problem that looks like this, gradient descent will have a much easier time here than here, right? I think you have seen some examples of that. If you apply gradient descent to something like this and you start in the wrong place, there's going to be a lot of zigzagging. But if you apply gradient descent here, you don't zigzag. So gradient descent is, and this has to do with the affine invariance of Newton's versus the lack of affine invariance of gradient descent. So these are the same for Newton's method, but not for gradient descent. Okay, maybe I should say after rescaling, the level curves could look like this. So conditioning is a key kind of difference between Newton and second-order methods and first-order methods. But of course, Newton's method is a more involved, it requires more involved, say, implementation. So in terms of, say, potential bugs or numerical errors, Newton's method, in principle, could have a little higher fragility. So that's kind of a first kind of high-level comparison of the two classes of methods. If we look at yeah, question.
Is there a stochastic version of this method?
Let's see. There is something that you can. It's not as. So there are some versions that include some kind of stochastic elements, but it's not as straightforward and it's not as popular as gradient. Okay. So in particular, I have seen relatively little of that, but that could be a limitation of my knowledge. But my general impression is that in terms of, say, stochastic methods, that's much more pervasive among first-order methods than second-order. But again, in principle, there is some possibility of stochastic methods for stochastic version for Newton's method. Now, because of these different matters of overhead in terms of memory and computation, if you were to do a more fair comparison of, say, gradient descent versus Newton's method, like back to that example of the logistic regression. So if we compare them, and in the horizontal axis we look at time instead of iteration count. If we look at time, we see this kind of behavior, and this is interesting because this is, in some way, this has justified the enormous popularity, the enormous surge of popularity of first order methods in recent years, in the last decade or so, is that if you want modest accuracy, then first order methods may actually be preferable to second order methods. If you're okay with relatively modest accuracy. But if you want to have high accuracy, right? So if you want to really get low in this axis, then generally second order methods will eventually prevail, because first order methods, they will be slow to get high accuracy. So the picture kind of reflects that, that we have, if we take into account, say, time, so progress in the algorithm versus time. All right. Now, if we look at beyond high level, if we take into account now the structural problem, and this, again, is something that is going to, we are going to see more of later on when we look at interior point methods, then if we have a way of exploiting certain, say, sparsity structure or similar kinds of structure, then that may allow us to set up the Hessian and solve the system of equations to compute the Newton step much more efficiently. So in certain kinds of problems, this could be maybe close to linear, or if not, certainly much cheaper than a cube price. So for example, we will see problems where maybe it's a composition like this. I think in the homework you're going to see something similar. You have a composition like this. So G of the relevant variables depends on some scaled version of your variables. Then the Hessian has this kind of dependence. So if this guy in the middle, if the Hessian of F is a simple type of Hessian, for example, it's a diagonal Hessian, then the entire Hessian for G would be manageable. Okay? And sometimes you can also use duality. So I think I'm almost out of time. Let me just take a minute to describe something real quick here, and I'll probably wrap this up next time because this is important. So one last thing that I want to say about Newton's method, I have about another minute, right, or two. Okay, so let me mention this real quick. So far we have spoken only about unconstrained Newton's method, but we will look at this case. This is an important case. If we look at the linearly constrained, we have linear constraints. We want to minimize a function subject to ax equal to b. So the most straightforward thing to do, the most obvious thing to do would be to think about ax equal to b as defining an affine space, and then just parameterize that new affine space and work on a smaller dimensional space. So that is, make a change of variables. Think about x as fy plus x0, where f spans the null space of A, and then just reduce the problem to a problem on y. So that's called the reduced space approach. And that's very kind of natural, but it actually has some, it comes with some kind of, you pay a price for that. Essentially, if you have a sparse problem, you lose a lot of structure when you do that. Then the most straightforward thing to do actually is equality constraint Newton. So let me define what that is. Equality constraint Newton is the following iterate. So if you want to do it with line search and everything already, x plus is x plus tv, where v is the solution to the quadratic approximation, but it is a constraint solution. It's a solution so that the next point is feasible. So it turns out that if you look at the KKT conditions for this problem, the KKT to solve that, to find v together with some w is the solution to this guy here, which has a remarkable interpretation. And I like to end with this because I find this to be really neat. So you can think about v. This is the step for with equality constraints, again, as minimizing that quadratic function subject to those constraints. That gives you this equation here, this system of equations. You need to solve this system of equations. That turns out to be exactly the same thing that you get if you look at the optimality conditions for the original problem, the KKT conditions for the original problem, and you think about applying Newton's method, the root-finding version of Newton's method to this problem. This guy here is the Jacobian of this function. This is the Jacobian. So you can see Newton's method for equality constraints both as a constraint quadratic minimization or as root finding of the KKT conditions. So I'll pick up right here next time, and then we'll go with barrier method that is built on Newton's method. So let's stop there for